Welcome to Chemistry 111. So we're going to continue where we left off, talking about enthalpy values and thermochemistry. So this last little bit of the chapter 10 will have to do with how do we calculate our enthalpy of reactions and how is this going to be useful, and eventually how will we relate this to the lab we're going to do. So start by going ahead and switching to PowerPoint. Give that a second. There we go. Okay. So we recently talked about a couple simple facts. One, there's enthalpy values for everything. Any reaction you can think of, there's an enthalpy value for. We talked about how enthalpy is one of those properties that the more you have of something, the more energy you're going to get. So if I double all the reactants and double all the products, I would get double the energy as well. That's one of those extensive properties. And finally, talked about how, very briefly, how this is a property determinant on the direction of the reaction flow. If to flow from reactants to products would be an exothermic reaction, meaning a heat-releasing reaction, the flow from products back to reactants would be an endothermic or heat-absorbing reaction. And it would be the same energy backwards as forwards, just different signs. So one of the first things we're going to do is look at what's called Hess's Law. And this is the perfect example of why enthalpy is a state function. The idea is if each reaction can be described by a specific enthalpy, can we combine reactions to understand a complex situation? And Hess's law states that if we combine two or more reactions together, the sum of the reactions, the enthalpy of that will be a sum of the enthalpies. If we double reaction, we would essentially double the enthalpy. If we would reverse a reaction, we would reverse the sign of the enthalpy, essentially multiply by -1. Basically saying here, if I take this basic reaction, methane, which is CH4, burns with oxygen to form CO2 and water. The energy associated with that is -889. If I were to double that, I'd be doubling the two methane particles, the two oxygen atoms or molecules, I'll be doubling the carbon dioxide, and I'd be doubling the two water molecules. I'd also be doubling the associated with that. So 2 methanes and 4 oxygens goes to 2 CO2 and 4 waters. That right there, I've doubled everything. I've also doubled my enthalpy. I'd get double the amount. If I look at as an example I gave here with water, H2 plus O2 goes to 2H2O, would have -286 kilojoules. Actually, and if I reverse that, so I'd be multiplying by -1. How would you make a negative number positive? You would add it to both sides, thus causing it to cancel out. Essentially, like this. If I had x minus 3 equals 0, let's jump back, x minus 3 equals 0, I can isolate the x by adding it to both sides. That cancels out, and I'll say x thus equals 3. The same way, if I have negative H2 and negative O2 yields negative H2O, adding 2H2 to both sides essentially cancels that out. I get H2 on that side. If I add O2 to both sides, that cancels O2, the negative O2, and gets it to the other side. If I add 2H2O to both sides, it cancels out the negative, and that essentially puts the reaction in the reverse way. Essentially flips the direction of the arrow. Instead of going from left to right, we could look at it as going right to left. But when we make it negative, we're reversing the sign. We are reversing the sign. And so instead of going reactants to products, now we're going what was formerly products back to reactants. But so when we reverse the direction arrow, we're also essentially reversing the sign of the enthalpy. If it gave us 286 energy, to go the other way would cost us 286 energy. This is the basic concept behind Hess's law. But what we're going to do is use this for some complicated reactions, specifically for some reactions that are a little bit harder to calculate. Take, for example, the formation of glucose. Simple sugar should be the simplest thing to calculate in the world. How would you get the energy of glucose, the sugar, by taking 6 carbons, 6 hydrogens, and 3 oxygens to make a C6H12O6? This basic building block of life, how much energy would it take to form this? Well, it seems like this should be a little simple, but in reality, there's no direct reaction that's going to give it. So we cannot simply take these things, throw them in a pot, and measure the energy. We can't measure the energy by a simple reaction. This is a reaction we should know, but we can't measure it directly. So what we can do is measure it indirectly by looking at 3 simpler reactions that have a direct product that we can measure. Carbon plus oxygen goes to CO2. We can do that one. We can burn that, no problem. It has an energy, negative 393.5. Hydrogen plus O2 goes to H2O. That's negative 285.8. And this one, we can take already built glucose and burn it. When we fully caramelize this back to CO2, fully combust it, CO2 and water, it produces negative 2805 kilojoules per mole. So I'm going to find a way to add these 3 equations together to get this above equation. Remember, the important thing is that you figure out how to get 6 carbons, how to get 6 hydrogens, how to get 3 oxygens, how to get 1 glucose. If you do this right and you add them all together, every non-essential molecule will drop out. Every CO2, every H2O will drop out, and you'll be left with only this if you've done this right. So the first thing you need to do is figure out how to combine these reactions. So I see the first thing here is there's 6 carbon. Is there any reaction that has carbon as a reactant? This first guy. This is the only reaction of the 3 available that has carbon as a reactant, or carbon anywhere in the equation. So I know this first reaction will be the only source of carbon. Now, because there's 6 carbons in the above reaction, I need to use this reaction 6 times. The same thing holds true. Reaction 2 is the only source of H2, the only source of hydrogen. And because of that, I need to use this reaction 6 times. Now, reaction 1, reaction 2, and reaction 3 are all sources of oxygen. So those are not going to be necessarily the thing to worry about there. What is going on? So we can't really use those as our source of oxygen. We'll worry about the oxygen later. But the last thing to note is we need glucose in the product side. We need glucose as a product. Reaction 3 is the only reaction that has glucose anywhere in there. So we'll need to use this once, but we have to reverse this reaction. We have to reverse it, so we'll do the opposite reaction. So I'm going to sum up these 3 situations: 6 times the reaction 1, 6 times reaction 2, and -1 times reaction 3. What we have here, 6 oxygens over here cancels with 6 oxygens over there, leaving there's only 3 oxygens left. That's going to carry down. 6 carbons, 6 hydrogens, those are going to carry down. 6 CO2s over here cancels with 6 CO2s over there. And 6 waters here going to cancel with 6 waters there, leaving us with the following reaction: 6 carbon, 6 hydrogen, 3 oxygen goes to glucose. So that is the reaction we want. We know what we have to do to the delta H's. So delta H1, which is 395, we multiply by 6. We get that number. Delta H number 2, which is -285, we multiply by 6. We get that number. -2805, we multiply by -1. We get that number. And then we added all 3 of these equations together, so we add all 3 of these delta H values together. And you would get how much energy would you get from forming glucose? You would get -1271. That's how much energy would be produced to form glucose in its standard state. The formation of glucose is an exothermic process. This is the most complicated equation we could really deal with. A better equation, let's see, I want to see what's on the next slide before I start going too much. The better equation would be this slide. This is something that I've often done in lab. I don't think we're doing this one in this lab, but this is an equation you might want to figure out in lab. If I mixed a base, ammonia, with an acid, nitric acid, how much energy would you get if it suddenly formed a solid that crashed out of solution? How much energy would it get when you put these 2 together and formed a solid? Now, there's a problem here. 1, acid plus base typically makes water and a salt. 2, all ammonium salts are soluble. All nitrate salts are soluble. So when I mix these two together, they should not suddenly precipitate from solution. So this is kind of a hard reaction to figure out. That's kind of a hard reaction to figure out. But we can figure it out by two reactions we can do. We can mix nitric acid and ammonia and see what is the result. The result is ammonium and nitrate. And I can dissolve ammonium nitrate in water, and that would form ammonium and nitrate. So in which way are we going to combine these two equations together to get this guy? So what we're going to do is, so we look. I have ammonia, I have a nitric acid. Where's the only reaction that has ammonia and nitric acid? Equation 1. So how are we going to have to use equation 1 to get those guys? We multiply by the identity property 1. We're only going to need this equation one time. We have ammonium nitrate salt, or solid. Where's ammonium nitrate solid? Reaction 2. It is on the wrong side of the equation. So we have to get it onto the other side. How do we do that? We use that -1. We're going to reverse the reaction by multiplying everything by -1. So when we do that, I'm going to flip that around, but we're also going to flip the sign of delta H. So let's try to add those guys together. So looking at this, this one is a much simpler reaction, and we're going to be doing something very similar to this. So HNO3 plus NH3 NH4 plus NO3 minus, and that's -120 kJ. The other one, we have NH4 plus and NO3 minus gives you NH4 NO3 solid. Because we reversed it, the positive 25 becomes negative 25.7 kilojoules. Now, as I add these together, everything that appears on left and right cancels out, just like we did with the spectator ions. So ammonium cancels ammonium. Nitrate cancels nitrate. We would get calculating HNO3 plus NH3 goes to NH4 NO3 solid. And so we would add negative 25.7 to negative 120. The delta H would thus be negative 145.7. That is a much simpler Hess's Law problem, but it's one you could directly see. What have I done? I flipped one reaction and I've added them together, and it gives us the reaction we want to solve for. And by doing that, we can find what would be the energy if you could make this reaction happen. What is the energy if you could make this reaction happen? And that is a perfect application of Hess's Law. Something that a little bit easier for us to understand. Now, this is essentially what we're going to do in lab. We are going to use calorimetry and Hess's Law to determine a reaction that is going to be a little bit harder to calculate for. We are going to mix a couple acids and bases together to determine what would this dissociation reaction be. We are going to first test out the calorimetry of the coffee cup, hot water plus cold water, and see what temperature they change to, and measure how much heat does the coffee cup absorb. Next, we're going to mix strong acid with strong base and see how much heat does the strong acid, strong base scenario absorb. Finally, we're going to mix weak acid with strong base and see how much heat is absorbed. And by that, we're going to be able to figure out how much heat would it absorb or release for just the acid to dissociate from itself in water, like break apart. That we're going to look at how much energy would acetic acid either have to gain or lose to split apart. But the reason we cannot simply look at that is because acetic acid is a weak electrolyte. It only typically breaks apart by, we'll say, 10%. So you measure 100% of an enthalpy if the reaction only wants to go to 10%. The problem is you can't, at least not directly. And that's where Hess's law comes in. If you can measure two reactions that go to 100%, then you can indirectly measure this reaction that wouldn't want to go to 100%. And that's what we'll be doing in lab. There'll be a lot of different math things, but I will be there to try to walk you through and try to help you every step of the way. So do not fear. Just because there's a lot of calorimetry calculations and some steps to keep in mind and this and that, I will be there to try to help you. Okay, so the last major concept here is going to be enthalpy of formation and enthalpy of reactions. So more often than not, enthalpy is applied directly to compounds, the formation of this compound. The enthalpy of a compound is essentially how much potential energy is stored within these bonds. And so oftentimes we'll see a delta H subscript F, which stands for the delta H for formation. It means this is the energy required or produced in forming 1 mole of this compound out of its component elements. So if I want to say how much energy is in methane, the question is, how much energy would it take to take 1 CH4 from 1 carbon and 2 hydrogen molecules? How much energy is stored in water when you take 1 hydrogen and 1/2 mole of oxygen? Now, because of this definition that we calculate the energy from making them from the pure elements, that the delta H formation of a pure element is, in its standard state, is always 0. If I say how much energy does it take to form carbon from carbon, the answer should be 0. That's how carbon is. That be how it be. If I say how much does it take to form oxygen from oxygen, you should say 0, because that's how oxygen is. If you say how much energy does it take to form ozone from oxygen, ozone is not the most common form of oxygen. It is not the most stable form of oxygen. And so that would be different. That would have a value. If I say how much energy does it take to form 1 atom of oxygen from a molecule of oxygen gas, the monoatomic oxygen, that would have an energy, because that's not how it exists. But for every pure element in the standard state, the value is 0. 0. So if I say chloride, chloride is different from chlorine gas. If I say sodium solid, that's 0. But if I say sodium ion, that has a number because that's not its standard form. So to make an enthalpy of formation, we would take the component elements and figure out how much energy it takes to form this. Because of the nature, 0 and 0, this has a number. We're just calculating this number. This number is associated with this number because the difference between 0 and 0 and that is going to be just that thing. So Mg plus O2 goes to MgO. The energy associated with MgO is 601. Now, there is a ton of enthalpy of formation values. They are all presented in the book's appendix. Not every single possible one, but a good chunk of them. When you do problems related to this, you are never expected to memorize any value except for pure elements, if at all. Why pure elements? Because pure elements are always 0. Yeah, it might be a trick question. What is the enthalpy of formation of carbon or something like that? Its answer is 0. Otherwise, in the homework, if you go into the hints, they will give you a link to these tables. It'll open up in a new window. You can find this online. You can go to Wikipedia, the standard enthalpy of formation values, and you can get all the values. All the test questions about these, I will give you a table of the values. You are never expected to memorize any of these values except for the standard element. But so how do we do this? So how do we calculate the enthalpy of a reaction? So we are going to look up each value of the enthalpy formation in the appendix. And what we're going to do is we're going to sum up all the products. We're going to sum up all the reactants, and we're going to take the difference between the two. Remember, how did we calculate a difference? It is always final minus initial. Final minus initial. So, because the products are the final state, those are the final energies. Because the reactants are how we initially start, those are our initial energies. So we're going to add up all the delta H formation for the products, all the delta H formation for the reactants, and subtract the two. So looking up here, delta H formation for the products, I'd look up. I have NaCl aqueous, I'd look up that. And it would be negative 407.1. I look up water, liquid. That'd be negative 285.83. I'd sum them up. Why am I putting that times 1? Because I have to take into account the coefficients. If I have 2 sodium chlorides, I'd have to add up that energy 2 times. If I were to have 3 waters, I would have to add it up 3 times. But given the fact that they're 1 and 1, I only need it 1 time. So the total number of products is negative 692.93. I look up HCl, aqueous, that's negative 167.2. Look up sodium hydroxide, aqueous, from the table, negative 469.6. I'd add those together. That's negative 636.8. So finally, I subtract 692 by 636. When I subtract a negative, it's the same as adding a positive. So I'm saying negative 692 plus positive 636, and the result is negative 56 kilojoules. So when I mix a strong acid and a strong base, it produces salt and water and a lot of heat. about 56 kilojoules of heat. The water should heat up when I mix them together. And that's something hopefully we will see in lab. But that's per kilojoule reaction. So if it takes 1 mole of HCl to react, you would get 56 kilojoules of heat. If I did 2 moles of HCl, 2 moles of base, I would get double that. But with this given reaction. So in a given thing, you would have a table like this. There may be more values than you need. Make sure you exactly match the value with what you're using, and you match the state. Water liquid is going to be different from water solid, which is going to be different from water gas. Carbon monoxide is going to be different from carbon dioxide. Make sure they match exactly from what you use on the table. So looking this up, let's do the products first. I'm going to see if this marker is any good. Yeah, it might be okay. I'll write this down before I switch it over. So, products. We have water liquid. That's negative 285.83. We have CO2 gas. Negative 394.4. And we have lead nitrate aqueous. Negative 421.3. Minus my reactants. We have 2 nitric acids. So negative 206.6 times 2. And 1 lead carbonate solid, which is negative 699.1. Not sure how visible this will be. I don't think that's very visible. I'll try drawing over in red. So 285.83, 394.4. So let's sum up all of my products. 7. Let's see. Let's see. 1, 5. Okay, let's see. 7. I think that's right. I'll have to double check the math in a second. So I'm pretty sure all the products sum up to negative 1101.53. Let's check that real quick. Plus 1101, yeah, 0.53. Good, perfect. That is the products minus the negative 206.62. Got to make sure you have the proper signage. Otherwise, this is going to be hard. So that's negative 4.2, negative 6.1. So let's see. 0.3, 2, 1. So 112. Let's see. I think that's right. Okay. So 112.3. Okay. So the sum of all the reactants is negative 1112.3. So I subtract this negative, same as add in a positive. So 1112.3 plus negative 1101.53. Sorry. We're going to get, these may be really big numbers, but when all things considered, the sum is going to be pretty small. You'd have a positive 10.77 kilojoules. 10.77 kilojoules when we all said and done. So when I mix these together, the solution gets a little bit colder. Not by much, but just enough, as it takes energy to break apart the lead carbonate. But so what did I do? I literally summed up all my products, summed up all my reactants, subtracted the two. It's not supposed to be super hard as long as you know how to do it. As long as you know how to do it. And that is the basic gist of this. That's the chapter. I'm going to wait a little bit before we start the next chapter. Let's see. I want to maybe pull up a few more example problems. Just pull up some out of whole cloth. So give me a second to look at that. Just because this is a kind of a big part of the chapter, it's not really we don't really have any other practice problems. I could go on to achieve, but that might take a little bit. Okay. Right now I'm just Googling the standard enthalpy of formation values just so I can get to a page where I can use them. Okay. Okay. Let's just do the standard. Let's see if I can. The trick is you have to make sure these values are present before you try to write an equation. If we don't have it, okay, this we go. So for those who are around for our chemistry week, we tried to do the barking dog reaction. The barking dog reaction produces the following results. We take dinitrogen monoxide and CS2, and we form N2 gas, CO2 gas, and elemental sulfur. So right off the bat, we're going to need 4 CS2s, 4 CO2. And if I'm not mistaken, we need 8 N2Os. But let's check. 8 oxygens, yes. That is now balanced. 8 N2Os, 4 CS2s, and it goes to 4 nitrogens, 4 carbon dioxides, and 1 elemental sulfur. So I have to look up on my phone. Obviously, I'm not going to be able to project it onto the screen, but let's start with looking up our values. N2O, gas. N2O is actually a particularly unstable gas. N2O has a delta H formation of positive 8205. That's strange. It's one of the few values that is positive. N2 is going to just be 0 because it's elemental. Elemental. Let's see. The only one I have to worry about is carbon disulfide. I'll look it up one way or another. I'll find that one. Sulfur. The basic thing, that's going to be 0. And carbon dioxide. Carbon dioxide. Oh, there we go. And carbon dioxide is so well known. It's 393.59. Here, right here, carbon disulfide is positive 89.41. 89.41. Okay. We have all the values we need. All the values we need. So with that in mind, the sum of all the products, negative 393.59 times 4 plus 0 times 4, it's 0, plus 0 times 1, also 0. That's pretty easy. So the sum of all the products is just negative 393.59 times 4. Negative 1574.36. The sum of all the reactants. Positive 8205 times 8. And positive 89.41 times 4. So this one's actually going to be a little interesting. That's going to be positive 1014.04. So I'm taking negative 1574.36 and I'm subtracting 1014.04. So, yeah. Subtracting. So I would get negative, as the answer, 2588.4 kilojoules. Basically a lot of energy. A lot of energy because essentially the two starting reactants are particularly unstable. That's what it means to have a positive enthalpy of formation. It, instead of being a potential energy storage well of we stored all this energy in the bonds and we released energy when we formed it, it took energy to make these happen. It took energy to make these happen. These are just ready to break apart on a moment's notice. These are not really stable. So then when we give it that spark, it produces a massive amount of energy as it chain reacts and breaks apart back down to its starting materials. So that is the main example I wanted to give. It's a perfectly good example. It produces a lot of heat, a lot of energy, and that heat, as it travels on the tube, is going to be building up for the big conclusion, which creates a vibration, a sound wave that we see is the barking dog. So now I don't really think we have enough time to maybe start next chapter, but the final chapter that we'll discuss is the gas chapter. We will go ahead and start that on Wednesday. In the meantime, once we get done with all the materials, we will definitely do some review. We will look at some of the achieved problems. We'll actually maybe work through some of them. We'll have test 4. We'll start reviewing for the final. Maybe I'll throw some slides together and we'll get a preview of next semester, but mostly it's just going to be a review and we'll figure something else out. Maybe go back and work through some of the old homework problems. Right now, this is where we'll stop for today. Thank you for your time, and I'll see you on Wednesday.